We discussed about reusable test bench. To create such reusable test benches, you need to understand the verification environment architecture. Let's look at the details. DUV. DUV is nothing but design under verification, or sometimes people call it as DUT, design under test. The important thing is DUV is a digital component. It can understand only binary. The input is binary, output is also binary, and whatever that happens within DUV, everything is going to happen in terms of binary. And the interfaces are protocol based. Interfaces are nothing but ports, input ports and output ports, and all the interfaces will be based on certain protocol. Mostly we use standard protocols like AXI, AHB, SPI. That's how the binary values will be driven to DUV. Alright. Environment. Environment is totally different from DUV. We call the environment as transaction level model. Everything is going to happen within the environment in terms of packets. So in verification, we use two terminologies. One is transactor, the other one is transaction. Transactor is nothing but test bench component, and transaction is nothing but data packet. Let's look at environment. It's called as verification environment. It's a top level test bench component. Basically, this top level test bench instantiates the lower level test bench components called transactors. All the transactors, drivers, monitors, generators, scoreboard, all the components will be instantiated within environment. And we connect all these components with the help of mailbox. Here there are two things. One is interface, the other one is mailbox. We use mailbox to connect the test bench components, and we use interface to connect the test bench component with DUV. Alright. Generator generates packets, random packets. It sends packets to the driver like this. Drivers convert packets into binary. Here there are two drivers. One is write driver, the other one is read driver. We also call the drivers and monitors as BFM. BFM means bus function model. Any test bench component which is connected directly with interface is called as bus function model. What it means is the test bench component which runs on bus is called bus function model. Alright. Drivers convert the packets into binary. Here the environment is TLM, so everything will happen in terms of packets. We cannot send packets directly to DUV. We need to convert the packets into binary values. That's what the driver does. Also, the driver follows DUT protocol to drive the values. Look at here. It gets the packet from the generator, and then it converts the packet into binary values. Also, it follows the DUT protocol to drive those binary values. When it's done with the packet, it also informs back to the generator, yes, I have completed the packet, you send me the next packet. So it takes care of the handshaking protocol also. It collects the packet from the generator, it converts the packet into binary, it drives all the binary values as per DUT protocol. So obviously the driver is going to be time consuming because it has to follow the DUT protocol. Definitely there will be time consumption in terms of clock cycles. Once it's done with the packet, it informs back to the generator to send the next packet. Monitor. Monitor is just opposite to driver. It converts the binary values back into packet. It also follows the DUT protocol. Here, the monitor is also connected with both the interfaces. And this is the methodology we follow. For every interface, we connect driver and monitor. Here there are two interfaces. write interface and read interface. So we have connected write driver and write monitor with write interface, and read driver and read monitor with read interface. This is very similar to UVM framework. To write even SystemVerilog test bench, we follow this standard methodology. For every interface, we connect driver and monitor. All right, look at the details. The generator generates packet. The packet will be converted into binary. That's what the driver does. When the driver drives the binary values, the same values will be collected by the monitor. This is write monitor. So whatever the packet that goes into driver, the same packet comes out of write monitor. The same thing happens for the read interface. Read packet will be sent to read driver. Read driver converts the packet into binary values. When it drives the binary values based on read protocol, all the binary values will be collected by the monitor and it produces the same packet back. But in case of read, there will be some output data also from DUV. So this read packet will be different from the driver packet. It depends on the protocol. All right. And the monitors will be connected with the scoreboard. What is scoreboard? Scoreboard is the test bench component which compares the data. So here, the scoreboard compares the output packet with a reference packet. Write monitor produces the write packet. The write packets will be stored in the reference model. And whenever the read monitor produces the output packet will be compared with the expected packet. That's what the scoreboard does. It compares the output packet with a reference packet. If the comparison is going to be successful, then it will generate pass message. If the comparison is going to fail, then it will generate error message. There will be coverage model also. Basically, this coverage model generates the functional coverage. We will explain the details how we can implement the coverage model in SystemVerilog later during the language course. But what you need to understand is we generate functional coverage for every test case. If the comparison is going to be successful, then the functional coverage will be generated. And with the help of functional coverage, we would be able to identify how much we verified in terms of functionality. So in this case, the DUV is there. There may be multiple design features. There could be 20 features or 40 features. Then the question is, have we verified all the features? So we track the progress of simulation with the help of functional coverage. Here, the environment has all the components: generator, all the drivers, monitors, and the monitors will be connected with scoreboard, and the scoreboard will have all the components like reference model, comparison logic, and coverage model. So the environment is the top level component which instantiates the lower level components. We call this environment as a reusable verification environment. On top of this environment, the test case writers will be writing different kinds of test cases. So here, what the test case does, the test case configures the environment. Before running the simulation, basically the test case writer is going to configure the environment with certain parameters. We discussed about different scenarios. Whether we want to generate small packet, whether we want to generate big packet, whether we want to generate corrupt packet, what kind of packets and how many packets. That's how the configuration is going to happen. Also, the test case is going to run the environment. So once it gives the command to the environment is going to do the things one by one. Generator will generate the packet, the driver will drive the values, and the monitor will collect the packet. That's what's going to happen. So the test case is the one which is going to initiate the command. So it runs the environment. Also, When the data comparison happens successfully, then the test case is going to stop the simulation. This is how we create the reusable verification environment. Look at here. This is the architecture we follow. DUV is a digital component. This is environment. Environment is nothing but transaction level model, because everything is going to happen in terms of packets within the environment. And the environment has all the test bench components like generator, driver, monitor, and for each interface we create driver and monitor. You need to remember this framework. And the monitors will be connected with Scoreboard. On top of environment, the test case writers will be writing test cases, so there will be multiple test cases. Let's look at this example. Dual port RAM. The memory has two interfaces. One is write interface, the other one is read interface. Write interface has data, address, write control signal, and clock. Read interface has data out, read address, read control signal. And this is also based on clock. If you want to write the data into the memory, we have to place the data and address, and then we need to enable the control signal. It's going to happen at the POSIX clock. So the data will be written into the memory. If you want to read the data, then we need to place the address, and then we need to activate the control signal. Then it's going to read the data from the memory based on the address, and the data will be available on data port. That's how the memory works. It's a simple memory. Let's look at how we can create verification environment to verify this DUV. So in this case, the DUV is a memory. It's a digital component. And the DUV has two interfaces. One is write interface, the other one is read interface. And within the environment, we use mailbox to connect all the transactors. Transactors are nothing but test bench components. So we use mailbox to connect generator with driver, and monitor with reference model, and reference model with scoreboard, or monitor with scoreboard. How you want to implement the data flow, based on that we can make the connections, and the connections will happen through mailbox. When it comes to connecting any test bench component with DUV, we have to use interface. So here, this is environment transaction level model, this is DUV, and on top of it there will be test cases. Let's look at the data flow. The generator is going to generate a write packet and then read packet. So write packet, let's look at the write interface. The packet reaches the driver. So in this case, the address is 1000 and the data is 100. It's going to convert the write packet into binary values. Look at how the data flow happens. Within DUV, the data will be written like this. Address is 1000 and the data is 100. When the binary values flow through this write interface, the same values will be collected by write monitor, and the write monitor produces the same packet, and this will be stored in the reference model. So whatever the packet that has gone inside write driver, the same packet comes out of write monitor. Absolutely no difference in this case. All right. Now let's look at the read interface. Read packet. Here if you look at, there will be only address. Address is 1000, and when this packet, let's look at the reference packet. When this packet reaches the reference model stores the value. Address is 1000 and the data is 100. That's what's stored in the reference model. You look at this. This is the reference model memory. Now look at this read interface. the packet will be converted into binary, so address will be driven. Now based on the address, it gets the value whatever is stored within DUV. The data is 100 and this packet goes to read monitor. Now if you look at this read monitor packet, it has got DUV data, right? Then the scoreboard gets this output packet. Also the same packet will be sent to reference model, and what happens is based on the address, the reference model will produce the data. So here the address will be used as packet ID. Let's say the reference model has multiple data. Then which data we want to use as reference data? Based on the address, we find the expected packet. So here the reference packet will be collected from the reference model, and then the scoreboard is going to compare the output packet with reference packet. That's how the data comparison is going to happen. And if the data comparison is going to be successful, then the coverage will be generated. This is how the environment works. Here there may be a question. Whatever the packet that goes through driver, the same packet comes out of monitor. Then do we need to have this monitor? It's kind of time consuming and it could be even redundant. Here, if you look at this packet, the packet that comes out of monitor, there is no difference between the monitor packet and driver packet. Absolutely no difference. Then why we need to have this monitor is the question. Can we connect this mailbox directly with the reference model? Here the challenge is we need to monitor the DUV interface. For example, whatever the packet that's generated by the generator, it might not reach DUV. We might not send all the packets to DUV. Sometimes we might drop some of the packets in the driver. Let's say the generator generates 10 packets. The driver gets all 10 packets. In driver, we can look at, okay, out of 10 packets, we find only 2 packets useful, remaining 8 packets not really good for verification. So we can even drop the packets also. So when we drop the packets here, the input will be 10 packets, but the output of driver would be only 2 packets. In that case, if we take all the packets to the reference model, there will be data mismatch. Can you visualize this? So we don't want to take all the packets directly from the generator for data comparison. We don't want to make connection like this. You can connect generator directly with the reference model because the same data goes to driver. But the point is the driver might drop some of the packets also. So it's good to sample the DUV interface always. When it comes to collecting any reference data, when it comes to collecting the output values, we always need to sample the DUV pins. So the methodology says whenever you come across any interface, you connect driver and monitor with the interface. So here, write interface, write driver and write monitor. Read interface, read driver and read monitor. That makes you safe. All right.